Hi, Bria. So when it comes to probability distributions, there are many different types, but in our class, we've only looked at two types, which is a probability distribution that has a uniform distribution, and then also the one that we're going to focus on in this class, which are distributions that are normally distributed. So data that has a normal distribution. So data that has a uniform distribution, its probability distribution or the graph of its probability distribution always looks like the shape of a rectangle. And the reason for that is because every single possible outcome for a uniform distribution has the same probability of occurring. So for example, in the waiting time at the airport, we are told that uh, people arriving at JFK at the checkpoint wait between 0 and 5 minutes. So their waiting time can be anywhere between 0 and 5 minutes. And hopefully you'll see that between 0 and 5 minutes, this is a continuous variable, which means that in between 0 and 5 are many other possible waiting times. So maybe you wait 1 minute, but it's possible that you have to wait 1.25 minutes, or maybe you wait 1.99 minutes, okay? So it doesn't have to be a whole minute. But the idea here is that your total waiting time is anywhere between 0 and 5, and they all occur with the same probability. So your chances of having to wait 1 minute are the same as your chances of having to wait 1.25 minutes, or your chances of having to wait 4 minutes is going to be the same as your chances of having to wait 5 minutes. So because every possible minute between 0 and 5 minutes has the same probability of occurring, you can see here what I've drawn is I've drawn a whole bunch of frequency bars for each possible wait time, and the frequency bar all have the same height. So the height, so I'll call this the height of the frequency bar, represents the probability of having to wait that long. So the other big idea that you have to make sure you understand about probability distributions is that when I take a look at all the possible outcomes and I take a look at a total of all the probabilities, right? Imagine that this blue shaded region that I just shaded in here is made up of an infinite number, okay, of frequency bars, each frequency bar corresponding to a potential time between 0 and 5 minutes. All right, and that entire blue shaded region has a total area of 1 because probabilities are numbers that are between 0 and 1. So we say here that the total area under the curve is equal to 1. And the area under the curve is also the same thing as the probability distribution. So it's also the same thing as the probability for each possible waiting time. Okay, so let me just label here, this is your wait time, measured in minutes. Okay, so your question is, how do we find out that that height of those frequency bars or that probability is 0.02? Well, using the idea that we know that the total area under the curve is equal to 1, notice that the blue shaded region also represents the area of a rectangle. And we know that the area of a rectangle is length times width. So if we take a look at this rectangle, hopefully you can see that we'll call this the length, is 5 units. All right, the width, I'll call it W. We don't know what it is yet, but you can see that it's going to be 0.2, so I'll show you where that comes from. All right, and we know that the entire area, when we take the length and we multiply it times the width, is equal to 1. So here I have an equation where I can solve for W, which is going to be the width of the rectangle, also known as the height of these frequency bars, okay? So to solve for W, I'm going to divide both sides by 5, and then hopefully you can see that 1 divided by 5 is 0.2. So that's where we got that probability from. So while we're on this topic, just real quickly so that you can see the difference between a normal distribution and a uniform distribution. A normal distribution would be a distribution where your possible outcomes, so let's say that these are all, we can also say they're waiting times, they don't occur at the same frequency. So at the center, so let's say that the average wait time, right, occurs at a high frequency, and then as the wait time gets longer and longer, right, the frequency gets smaller and smaller, and as the wait time gets smaller and smaller, the frequency also gets smaller and smaller. So here you can see that the frequency bars are not all the same height, meaning that, so if X, again, if we call this the wait time, we see that your wait time, it varies, okay? So maybe I'm going to make up some numbers here. So let's say that, you wait 10 minutes. So we say that 10 minutes is the average wait time, and it's probably the most typical time since it's got the highest frequency here. It's the average wait time for the checkpoint. But then we take a look and we say, well, what's the probability that you have to wait, 11 minutes or 12 minutes or 13 minutes? So as the wait time gets longer, you can see that the probability of having to wait that long, the probability starts to decrease. And then we take a look at, well, what's the probability that you have to wait less than 10 minutes? So let's say 9 minutes or 8 minutes or 7 minutes or 6 minutes. Also, you can see that the frequency bar gets lower. So that means that the probability that you wait less than 10 minutes is also decreasing. And so here, hopefully you can see that you have that bell-shaped curve. But the big idea here is that the entire area under this bell-shaped curve, it also has a total area that adds up to 1. So its total area is also, so total area under the curve is also equal to 1. And we also correspond those areas with probabilities. I hope that helps.